Hello everyone, this is Dr. Speights with Math Videos on PowerPoint. In this lesson, we're going to identify basic parent functions. We're also going to use the parent functions to perform transformations. Let's begin by going over key vocabulary. Basic functions are called apparent functions. And in this section, we're going to do several types of transformations with these parent functions. A transformation is a change in position, size, or the shape of a graph or figure. An example of a transformation would be a translation, meaning a slide. Now that can be a slide to the left or slide to the right. It can be a slide up or a slide down. Another transformation is a reflection. A reflection is nothing more than a flip. You can flip an object or a shape across the x-axis, and you can also flip it or reflect it about the y-axis. Also, the original figure is often called the pre-image, and the new image is often called the image. So here are the basic parent functions. I suggest you familiarize yourself with these functions because you're sure to see them on the test. So the constant function is first, which is a horizontal line. Then we have the linear function, also known as the identity function. Then we have the quadratic function, which is a parabola. We have the cubic function, which is like an S shape that is faced up. Then we have the square root function, our cube root function, which is like the S shape, but it's on its side. We have the absolute value function, which forms a V. And we have the greatest integer function. And here is a summary of the transformation rules. Let's begin with a vertical translation. A vertical translation is a slide up or down. So if you have the function and you notice in the back you have a plus some number, that means the graph of that function will shift upward. If you see a minus some number behind the function, that means the graph of that function will shift downward. In this example here, you see the original graph, and then you see the graph shifted 2 units upward. That's why you see the +2 there in the back. The green graph, notice it will shift 3 units downwards. That's why you see -3 there in the back of that function. Let's take a look at the parent function, the quadratic function, f of x equals x squared. And we're asked to transform that graph to g of x, which is x squared plus 2. So notice this is nothing more than the quadratic function, and in the back you notice a +2, which means we're going to shift this graph 2 units upward. So when we do so, it's going to look like so. So here we have a parent function, f of x equals the square root of x, the square root function, and we're asked to transform this image to g of x, which is the square root of x minus 3. And because we see a -3 there in the back of the function, indicates that we're going to shift the graph of the square root function down 3 units. We can achieve this by simply taking any 2 or 3 points on the graph and simply shift them down 3 units. When we do so, it's going to look like so. And now let's move on to horizontal translations. A horizontal translation is a shift or slide to the left or to the right. You'll know a horizontal translation because the number that tells you how many units you're going to move to the left or to the right is within the function itself. Now, everything about horizontal is not as it seems. So when you see x minus k, you may think that you're going to move to the left because you see the minus sign, but you're actually going to move to the right that many units. And when you see x plus some number, although you may think that you're going to move to the right because there's a plus, you're actually going to move to the left. And here's why it has that opposite. When you look at the form x minus k, k being some number, this is understood that the number is positive when it's in the form x minus k. And because it is a positive, we are going to move to the right. However, if you have x minus negative k, and now your number is understood to be a negative, and because it is a negative, you will move to the left because it's a negative. Now, when you write that x minus negative k, it looks like x plus k. But again, because that k is negative, so therefore, again, when you see plus, you will move to the left. Now, let's move on to give me just a moment here. If you take a look at this graph here, you'll see that the blue is the original graph. And then within the function, you see x plus 2, and it was moved 2 units to the left. X minus 3 was moved 3 units to the right. Let's look at the parent function f of x equals the absolute value of x. So here we have the absolute value function, and we're asked to sketch a transformation of that, the absolute value of x minus 4. And notice that the number is within the function, which means this is a horizontal shift. And recall that x minus some number means that the number itself is positive, which means you're going to shift 4 units to the right. So when we do so, it's going to look like so. And again, you can achieve that by simply taking a few points from the parent function and just move them or shift them over 4 units to the right. In this next example, we're going to use the parent function f of x equals x squared to sketch the graph of g of x equals x plus 3 quantity squared. So notice that our number 3 is within the function, so therefore it is a horizontal shift. And when you see x plus some number, that's meaning that the number itself was a negative, and that's how you got the positive. So that means we're going to move 3 units to the left since the number itself is assumed to be negative. So 3 units to the left, all we have to do is just grab any a few points on the parent function graph and shift them over 3 units to the left. When we do so, it's going to look like so. And there you have it. And now let's talk about reflections. Reflection is nothing more than a flip. It is a mirror image of the image across a line. So in the first example here, we see that the image was reflected across the x-axis, and that's like folding a paper the short way. When you fold it, it's a mirror image there. To the right, you'll see that the image was reflected about the y-axis, so it was reflected across y, which means the same thing as if you were to fold the paper the long way, you would see a mirror image of it. In this example, we're going to use the parent function, the square root of x, to reflect the graph about the x-axis. The transform graph, as you can see, g of x equals the negative square root of x. How do you know that you're going to flip it or reflect it about the x-axis? When you see the negative outside in front of the function, you should know that you are reflecting that image about the x-axis. And to do that, all you have to do is take a few points from your parent function graph and change the y values to their opposite. So for example, let's take a few points here on the graph. We can take the ordered pair of 1, 1 and the ordered pair 4, 2. Let's just work on those two. So if we take these ordered pairs and change the y values to their opposite by placing a negative in front of them, you're going to see that when we flip the image across the x-axis, these points will then be on the graph. So if you'll give me just a moment, let me put the pen back there. So let's go ahead and flip the image across there. Let's look for the first point there of there you have it. The image is flipped. Now let's see if these points are on the graph. So over 1, down 1, sure enough, it's there. Over 4, down 2, and it's there. So again, to reflect an image or graph about the x-axis, all you have to do is change your y values to their opposites. Reflection about the y-axis. In this example, we're going to use the parent function f of x equals the square root of x to sketch the graph that has been reflected about the y-axis. So notice g of x equals the square root of negative x. Notice the negative is inside within the function there in front. So to reflect an image about y, all you have to do is change the x values to their opposites. We can actually use the same points we did in the previous example, and that was the ordered pair of 1, 1, and the ordered pair 4, 2. And again, to reflect it about y, all we need to do is change the x values to their opposite by placing a negative there in front. And now let's go ahead and graph that or sketch our graph and see if these points are indeed on our graph. So we have the y-axis there, and we're going to now sketch the graph over the y-axis. When we do so, it looks like so. All right, let's check to see if those points are on our graph. So the first one is over 1 and up 1. Yes, it is. The other one is over -4 and up 2. And yes, it is also there. So again, when you want to reflect an image about the y-axis, all you have to do is use the parent function, take a few points from there, and change all the x values to their opposite. And now let's discuss a dilation, which is a stretch or compression of the graph. A compression is also known as a shrinking as well. A vertical stretch and a compression. Now, a vertical stretch is like you pulling up on a graph. Like if you were to grab hold of the graph and pull it upward, you're pulling it away from the x-axis. That's a vertical stretch. And that same graph, instead of pulling up on it, if you push down on it, you're like pushing it down toward the x-axis. That's a compression or shrinking the graph. So here we're asked to use the parent function f of x equals the square root of x to sketch a graph that is stretched by a factor of 2. And you know that it's stretched by a factor of 2 because if the number outside, which by the way, if it's out there in front, that is a vertical stretch or compression. If the number is greater than 1, it is a stretch, such as in this case, stretched by a factor of 2. If the number is a fraction between 0 and 1, then it is a compression. So what I want you to see though is if you take a look right now on the screen, you see the parent function, the square root of x. And in a moment, I'm going to show you what it looks like when the graph has been stretched by a factor of 2. It's going to look like so. And basically what's happening here, notice, is that it pulls each point away from the x-axis, this vertical stretching. A vertical compression, on the other hand, again, when you notice that a number is between 0 and 1, meaning a fraction there outside, that is going to be a vertical compression, which instead of pulling up on the graph, you're pushing down on it and you're pushing it toward the x-axis. So when you do so, it's going to look like so. Notice the graph is shrunk by half of what it was. And now let's discuss horizontal stretches and compressions. A horizontal stretch or compression is you're going to be pulling or pushing the graph either toward or away from the y-axis. In this example, we're asked to use the parent function to sketch the graph of f of x equals x squared. In other words, the quadratic function. And notice with horizontal, it is always within the function itself. Notice it's there in parentheses and it's there in front. Now, the thing with horizontal, as I told you earlier, it's not always what it seems. So although you see a fraction here, and you may think of this as a shrinking horizontally, but it's not. It's actually a horizontal stretching. So if the number is between 0 and 1, then you have a horizontal stretching of the graph. In this case, it's like each point is being pulled away from the y-axis. So you're kind of like grabbing a hold to the two handles of the parabola and then pulling on them, pulling to the left and to the right, and it stretches it. And this happens again whenever you have a number there between 0 and 1. In this example, we're going to do a horizontal compression. We're actually use the parent function, the absolute value, to sketch the graph of the absolute value of 2x. And notice that the number is within the function itself, so that is a horizontal. In terms of is it a stretch or compression, if the number is greater than 1, then it is a horizontal shrinking or compression. So when we graph that, it's going to look like so. And what happens is each point is being pushed toward the y-axis. So a summary of the vertical and horizontal stretches and compressions will look like so. A vertical stretch, and you'll know a vertical stretch because you'll notice that your number will be outside and it will be a number greater than 1. This is like grabbing the graph and pulling upward on it. This is a vertical stretching. Each point is being pulled away from the x-axis. And if you have a number out there that is a fraction, a number between 0 and 1, it is pushing the graph down toward the x-axis, and this is a vertical shrinking or a compression. So horizontal stretch and compression. A compression, you'll notice it horizontal because it's within the function itself inside. If the number is greater than 1, then the graph is one of a horizontal compression, which means you're pushing each point toward the y-axis. And if the number within the function is a number between 0 and 1, then that is a horizontal stretching, which means each point is being pulled away from the y-axis. Let's do some practice on identifying the transformations of an equation. So first of all, if the equation is in this form, if you have a number outside, then it is a vertical stretch or vertical compression. If that number is greater than 1, it is going to be a vertical stretch. If that number is a fraction, it is going to be a compression or shrinking. If it is a negative, it will be a reflection about the x-axis. Next, we have the horizontal shift. If this number is positive, then you're going to move to the right. If this number is negative, you're going to move to the left. In the back, we have the vertical shift. If this number is plus some number, you're going to shift it up that amount of units. And if it is minus some number, you're going to shift it down that number of units. So what did we do to this function, the parent function here? If you said it was a shift down vertically 7 units, then you are correct. This was a vertical shift down 7 units. Who's the parent? What is the parent function here? If you said quadratic function, then you are correct. If you take all the transformations away, you are left with f of x equals x squared, which is the quadratic function. So what did we do to this function? Notice the negative is within and horizontal is always within. So this means that this was a reflection about the y-axis. And in the back, what do we have? If you said this is a vertical shift down 2 units, then you are absolutely correct. Now, can you tell me who's the parent? What is the parent function here? Take away all the transformations, and what are you left with? If you said the square root function, then you're absolutely correct. Good job. Let's move on. What did we do to this function? Again, remember, horizontal is always within the function, so this was a horizontal shift. And when we see +1, that means that this number was understood to be a negative, which means that it is shift to the left 1 unit. What else happened here? You got it. If you said that was a vertical shift down 3 units, then you are correct. And by the way, what is the parent function here? If you said cubic function, you are correct. When we take away all the transformation, we are left with h of x equals x cubed. What do we do to this function? What type of transformations took place? Again, horizontal is always within. And with horizontal, you have to be careful though with the stretches and compression. It's quite the opposite of what you think. And although you think this number is a number that's greater than 1 and it should be a stretch, it is actually the opposite. It is a compression or shrinking by a factor of 2. And what else happened here? You got it. If you said vertically we shifted the graph up 1 unit, then yes, you are correct. And what is the parent function here? Yes, you got it, the quadratic function. I see you catching on. So what do we do here? Okay, yes, the number is outside this time, so that is a vertical stretch or compression. And with vertical, if the number is greater than 1, it is a stretch. So this is a vertical stretch by compression, by a factor of 2. And what else happened here? Yes, you see that it's inside. Horizontal is always inside. And this was a shift to the right 1 unit. And who's the parent, by the way? Yes, you got it. Absolute value. And what do we do here? I think this is the last one. You're doing very well. Did you notice that negative outside up front? That's some type of reflection. Is that a reflection about the x or y? If you said x, that is correct. What else happened here? Hint, it's within the function, so it must be horizontal. So is it 3 to the left or is it 3 to the right? If you said 3 to the left, then you are absolutely correct. Lastly, what type of transformation took place? Yes, a vertical shift up 2 units. And who's the parent? You got it. That is the square root function. Excellent. Good job. I think you're catching on. And now, writing the equation of a transformed graph. So here we're going to use the parent function x squared as a guide to not only describe the transformation, but to write the equation of the function. So you notice in blue we have the parent function x squared, and then we have the graph here in red represents the transformed function. And I can see here that, yes, in terms of, let's take a look at what's outside with red. So outside red, it's not a negative because you would see the graph flipped across the x-axis, and that is not the case, so should not be a negative out there. Let's see if the graph was stretched or compressed in any way. Well, take a look at the parent function. One of the points is at 0, 0. I see another point at 1, 1, and then negative 1, 1. Let's see if we see those same points on the transform graph. So let's go over to the red graph. So we have the middle there of the parabola. And now let's move over. Let's see 1, 1. We're there. Negative 1, 1 is also there, which means that the graph in terms of its shape was not stretched or compressed in any way, so there should not be any number out here. Now the next thing we're going to do is we need to determine was there any horizontal translation going on, and as we can see, yes, there was. The graph moved from its center at 0 over to now it's at 2, and so that's 2 units to the right. And so remember, when we want to write that, that's going to be x minus 2 squared. Now let's see if there's any vertical translation that took place. Was it shift up or down? You bet it was shift upward. And let's see about how many. 1, 2, 3, 4. So in the back you're going to have a positive 4 because the graph was shifted up 4 units. So writing the equation for the transformed graph is going to look like so. Again, notice the graph was shifted horizontally to the right 2 and vertically shifted up 4 units. Let's do another one. In this example, we're going to use the graph of the absolute value of x as a guide to not only describe the transformation, but to write the equation for the transform function. So here we have the absolute value parent function, and first let's determine whether there's going to be any type of number out here. Was the graph stretched or shrunk in any way? Looking at the parent function, it's at 0, 0. Another point is at 1, 1, and negative 1, 1, just as the quadratic function was. Now let's look at the transform graph. Do we have those same? We have the center. We also have 1, 1, and we have negative 1, 1. So again, there was no stretching or compression going on. But next we need to look at whether there was any horizontal shift. Was it shift to the left or to the right? Yes, you bet. It moved from its point in the center there over to 1, 2, 3 units to the left. And when it's to the left, we're going to put, is that going to be x plus 3 or is that going to be x minus 3? If you said x plus 3, then you're absolutely correct. Now we need to determine the vertical translation. As you can see, The graph was also shifted down 2 units. So when we put all that together, we have a horizontal shift to the left 3 units, and we have a vertical shift down 2 units. So using our absolute value bars and to write our equation is going to look like so. So you have g of x equals the absolute value of x plus 3 minus 2. And there you have it. Okay, that's it for this lesson. I'm going to share one of my favorite quotes from Dr. Martin Luther King. He said, "If you can't fly, then run. If you can't run, then walk. If you can't walk, then crawl. But whatever you do, you have to keep moving forward." Thank you for watching math videos on PowerPoint with Dr. Speights. I hope you learned something. Please feel free to like, share, and subscribe. Bye-bye.